Hello, and welcome to Making Decisions, Decision Algorithms and Trees. My name is Tuesday Johnson, and this is an introduction to concept with applications. So a decision algorithm is a procedure in which we make a sequence of decisions. We'll use the addition and multiplication principles in the decision algorithm by imagining that we are designing an item so that we can determine the number of possible ways to do so. Now keep in mind, we're putting a mathematical structure on everyday life choices. Okay, so it is a little weird at first, but you got this. Decision algorithm can be illustrated by a decision tree in which the choices we make are represented by branches. And I'll show you one of those in the example 3. Okay, so Anna is deciding what to wear for her first day of college math. You know, it's such a big decision. She's narrowed the choices to shorts or jeans. If she wears shorts, she has 3 pairs to choose from, with 5 shirts to go with those shorts, and she always wears her sandals with shorts. If she wears jeans, she has 5 pairs to choose from, with 4 shirts that go with those jeans, along with 3 different pairs of sneakers that would complete the outfit. How many outfits can Anna make? Well, you might stand at your closet and just say, I don't know a lot, it's too many choices, but we could break this down mathematically. So she's decided shorts or jeans. So the first 2 sentences, the only thing I care about is shorts or jeans. Let's take a look if she chooses shorts. Alternative 1, she chooses shorts. She has 3 pairs to choose from. Once she chooses her shorts, then she has 5 shirts to choose from, only 1 footwear option, and she's going to wear sandals for that. What happens if she chooses jeans? So options, alternatives, shorts or jeans. If she chooses jeans, she has 5 pairs to choose from, and then she'll, next step, dress herself with the shirt. Final step, dress yourself with shoes. All right, so our steps will give us multiplication, and our alternatives are the addition principle. All right. If you care about matching your clothes, you start with one place, and then. So and then is going to be multiply, or options, alternatives, that's going to be addition. So how many different outfits can she make? 3 pairs of shorts, 5 shirts, and sandals. That's 3 times 5 times 1 is 15. Or, so we'll add 5 jeans, 4 shirts, 3 sneakers. 5 times 4 is 20. 20 times 3 is 60. And we will add these 2 alternatives to get 75 total outfits. You don't have to have a ton of clothes. You can make some good outfits. In 1966, the NCAA men's basketball tournament Final Four included the teams of Duke, Kentucky, UTEP, and Utah. Go Utes! How many different ways could the teams... I like Duke and Kentucky as much as I like Utah. Go Blue Devils and... Wildcats too. I'm just saying UTEP 1 picks up. How many different ways could the teams have finished the tournament if we are given the bracket as shown below? Well, if Duke was in the top seed and Utah was in the bottom seed, and this is not seedings in any way, that is not how it was, I'm just saying according to our diagram, then we could have had Kentucky and UTEP, or UTEP and Kentucky. So we have 2 options with how we could fill in this level of our bracket. Let's suppose UTEP played Utah, as I believe they did. So this is Kentucky. So what happens here? It doesn't matter. Does Duke win? Does Kentucky win? It doesn't matter if it was Duke or Kentucky. We have 2 choices, because if UTEP was here, UTEP won. What if UTEP wasn't there? Well, then UTEP would be here, and UTEP had to have won. So either way, we're going to have 2 choices for one of the blanks and only 1 choice for the other. These are steps, right? Final 4, and then semifinals, and finally the championship. So we'll multiply these numbers together to give us the answer of 4 different ways we could fill in the bracket from this point, including Duke, Kentucky, UTEP, and Utah, showing UTEP the 1966 men's basketball championship. Example 3. This Jack's a weird guy. Jack will have some odd situations. Here's Jack's first one. Jack decided to take his date to an ice cream shop. Jack noticed the decision-making process and decided to determine how many ice cream treats can be made with 1 scoop and 1 topping. Pretty sure his date was taking too long. First, you choose cone or cup. Then there are two types of cones, waffle or sugar, and 3 sizes of cup, small, medium, or large. After you get your base, you select from vanilla, chocolate, or strawberry. We're not a Baskin Robbins here, we're keeping it simple. And you follow with a choice of toppings. You can have sprinkles, chocolate bits, peanut butter bits, or none. We're not doubling up, no Reese's bits here. What value should Jack have come up with? Wow, English hard. If he was trying to make this in a decision algorithm. Now, the fact that Jack decided to take his date to an ice cream shop has nothing to do with this problem. That's just setup. You're going to find that a lot in these application problems. Put a line through it, right? Mentally cross it out or whatever. Jack noticed decision making. He wants to blah blah blah. Determine how many ice cream treats can be made with 1 scoop and 1 topping. Now, he didn't really mention the vessel, but right, it matters what we're putting it in. We're not going to eat ice cream out of our hands. First, you choose a cone or a cup. There are 2 types of cone and 3 sizes of cups. So this is a decision tree. So we start at the vertex, that's the beginning here, and we make a choice, cup or cone. At the second layer, all right, second layer of a decision tree. Now, if we chose cup, we have this series of choices, small, medium, or large. If we chose cone, now our decisions are sugar or waffle. And we can keep going. Next layer, what type of ice cream? Maybe you want to choose a cup that's small with chocolate, or a cup that's small with strawberry, or a cup that's medium with vanilla. All these different options, and this one actually goes here, but it would overwrite. It's chaotic, and you can see that as we grow more, it's going to be larger and crazier. I do not generally use Venn diagrams past a 3 level, even though this one would require 4 here at chocolate. Actually, at all of these ends, I would have sprinkles, chocolate bits, peanut butter bits, none. Sprinkles, chocolate bits, peanut butter bits, or none. So we see here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different ice creams that we could use just with our vessel and our ice cream. 15 times the 4 different toppings, 15 times 4. It seems like Jack should have come up with 60 different ice cream treats, even with this limited selection. So when you go to Baskin Robbins, 31 flavors, and it takes a little while for your kids or your spouse or whoever to make a decision, that's because there's a lot of decisions going on, a lot of them. All right. Thank you for watching this video. Be sure to subscribe to Math with Tuesday on YouTube for all of your math needs.